Okay. So I'm assuming, how many of you guys have read through 1.1
1.1.
and 1.2?
I've done 1.1.
Okay. And then how many of the exercises have you guys attempted so far?
1.1 or 1.2.
Okay.
Wait, which one? Which section?
Oh, either. Yeah.
I've done 1.1.
I have only done 1.1 for exercises so far.
Okay. So that, because I'm just trying to get an idea of what would be the most helpful to be helping you guys out
What's
with
the
today.
1.1?
1.1, 1.2 and 1.3,
Technically. Now that would mean
but with him gone, maybe not. At least 1.1.
at least
Yeah,
1.1
yeah,
and 2. I would definitely bet on 1.1 and 1.2. The only one in question is 1.2. So let's start with just a quick review. I know we technically covered this in class, but there's it's a really, really important definition that's going to go on for basically what we're doing is we're building up to groups, and groups are the kind of the first main structure in algebra that we're going to really take a lot of time to study. So let's see. Define a binary operation. And do we remember what a binary operation is? Like if you hear that, you have it, not just a mental image conceptually what that is, but the definition of a binary operator.
Mhm.
Okay, cool. So a binary operation star on F is commutative if and only if A star B equals B star A. And so this is super familiar to a lot of people when they first see this concept, because they think of addition, they think of multiplication, and we're told, in high school and other stuff, well, yeah, if you take two numbers and you add them, you can flip the order, you don't change. If you multiply two real numbers together, you can flip the order, doesn't change it. So this is a property of any operator, and what's great about an abstract algebra is that if you can define any operation, just any operation star on any set of things, so it doesn't have to be just real numbers, and then if you can show this property, then it's commutative. And then another definition is that a binary operation star on S is associative if and only if A star B star C is equal to A star B star C. Good morning.
Good morning.
So these two definitions, and especially if you've been working through the exercises, you had to know these really, really well. Otherwise, you just simply cannot answer certain exercises. We have, and I think we should add, this has to be true for all A, B's, and C's in this set. And I should also say the same thing here for all A's and B's in your set. Because if you can show that there's some combination, any combination, it only takes one combination that does not satisfy this to break it, basically. And so that's why this if and only if is a very, very strong statement. If you can find only one instance, one example, a counterexample to this, then it's not associative. So at the same time, these are very, very sensitive definitions because they have to be very, very precise. But when you do find something that is either commutative or associative, that's a very strong statement about your operation. It's a very specific type of operation. Okay, so let's work through the theorem. Okay, so theorem. So we're gonna let S be a set and let F, G, H be functions. Mapping S into S. Okay, so we want to show that then F of G of H is equal to F of G of H. So what are we essentially trying to prove? Or what is this theorem saying about if we have three functions that satisfies this?
Is the composition associative?
Exactly. So this operation, that like open circle, we use to denote the composition of functions. And so we don't have to take it for granted. This result is just a direct, you can directly compute this based off of the operation. So if you took some F of G of H, what does that actually mean? Well, you're taking S of, and then G of H, right? But what do we know about G of H? G composition H is really just G composition H. And so, yes, this might not be the kind of operator like a plus or a minus or a times or something like that, where it's, you kind of string it out and it interacts with what you have differently, but that's all right. It is still an operation. And then so we know what this side is. What about this side? So instead, if we start by taking F composition G and then take the composition of F after that, well, F composition G is just F of G of H. But then in order for this function to be a composition of this, we have F G of H again. So we can make a statement. We can say then for all F G H, mapping S into S, F of G of H is equal to F of G of H. And so this is basically the really, really fast way you can just prove this theorem really quick. And so what's going to happen is in abstract algebra, what's more important than your ability to do these explicit computations on explicit examples, obviously you need to know how to do that. Like an exercise is saying, did you understand the higher concept? And so when we bring the abstraction level down a notch to give you like, okay, instead of arbitrary sets, what if we just say set of 2x2 matrices with reals or something like that? And then that's when your prerequisite knowledge from other math courses comes in handy, because then you can then compute through exercises, you can verify the more abstract results from the fields. So as a note, how many of you guys have taken a proofs course before, like in maths?
Discrete?
Okay, so discrete is close. You get introduced to the set builder notation and the logic. But I mean like the writing of like proof writing.
College geometry.
There you go. Yeah, that's good.
I've been tempted to teach college, or not college, high school geometry. But it wasn't very good.
But yeah, those are still proofs, right? So
What about
the
calculus 4?
what?
What about calculus 4?
Yes. So
Pre-algebra.
I mean, it depends on your teacher, I guess. So the idea is what I'm going to cover a little bit today that's not in the textbook is algebra, proof writing, Okay, and so we're gonna do two types. I'm gonna introduce you to inductive proofs. Because I know that reading was technically assigned, but then we didn't do any exercises on it. But induction is very, very powerful. Let's see. So we want to prove. And actually, okay, so we're doing mathematical induction. And so what you're going to find when you do proofs for algebra, it's not necessarily you're learning how to do an explicit type of math. This is more the style and the kind of conventions we have for presenting your work rigorously, clearly, and then elegantly. Because at the end of the day, and so this is kind of what's funny, with the higher level you get in math, the more hours you spend trying to make your math look like a first grader could read it, really. I mean, at the end of the day, really, really well done hard math looks really simple. It doesn't look hard. And so that can be different from like computer science and from mechanical engineering and stuff, where kind of the more hours and the more time you spend into something more complex, you get the impression that it's going to look more and more impressive, right? The end result. We got to redefine the idea of impressive result as something that looks very elegant, very simple, very straightforward, something that should almost appear obvious, but wasn't to begin with. And so induction is kind of like the first thing that we do as a common strategy. And so we're going to try to prove that 1 plus 2 plus 3 plus and so on and so forth. So we get 2 plus n. Let's see, I think it was like n plus 1 over 2 equals n times n plus 1 over 2. So in other words, we're trying to prove the formula for the sum of the first n integers. And so I should specify n is an integer. It's a positive integer, because there's no point in taking the sum of the first 0 integers. We could do that. Actually, the proof works both ways. So let's include 0. Now, well, actually, no, that's a pointless exercise, because then you just multiply 0 by 0. Doesn't do anything. So the idea with induction is this very powerful idea. So what we do is, remember at the very beginning, he defined a statement. So we talked, what is a statement? Something that's true or false. So we define some statement and we denote it like this. No, this is not a function. And so it's not saying P is a function where n is the variable. This is saying, here's a statement with n, okay? We're trying to show that this is true for all n. So we want to show that this statement will hold true for all n. Now, we could obviously just start substituting numbers in, right? We could say, what about 1? What if n is equal to 1? Well, the sum of the first 1 integers is 1. And then if you end up plugging that into here, you get 1 times 2 divided by 2 is 1. So you say, okay, checks out. What about 3? Well, 1 plus 2 plus 3 is 6. And then 3 times 4 is 12 divided by 2 is 6. Okay, so it checks out. That's not a proof though. So that's showing that specific things are consistent for a formula, but you can't just write those two things down and say, and we're done. Because many times there's like this weird exceptions that can lie in a formula that breaks it, so then it makes it no longer true. So we're trying to show in induction that some statement Pn is going to be true for all n, regardless of what n is, so long as n satisfies this. So we're not including like n equals pi, because that is meaningless in the context of this. So how are we going to show that this is true if we have to do it for this broad sweeping every single n? And so what induction lets us do is it says, okay, if we can show that P1 is true, or some base case. So sometimes in a book, because they're kind of trying to make it abstract, they'll say some P of K is true. So if you can guarantee that 1, you're kind of like initial condition. So I'm assuming you've had calculus. It's a similar thing. It's like when you solve a differential equation. Then if you have that initial condition, you have somewhere to anchor yourself to. So we're anchoring ourselves down, and this is generally the lowest possible case. And so with our case, n's, we're going to have P of 1, because the smallest n that we're allowed to have is 1. And then if we can say, all right, we're going to, so this is step one. And then the second step, we assume that P of some K is true, where K is greater than the thing that we just started with. So in other words, we're assuming now that the general statement actually holds for the remainder of the K. And so something you're going to find when we do proofs in mathematics is that you will never be able to do anything without making an assumption. So the structure of any proof will contain at the very beginning assumptions, then definitions, and in combination, you reach conclusions there. But you can never, we couldn't just get here to the result without making a very, very key assumption. And in the case of induction, this assumption is that the PK is true for everything past your initial tested value. And so now, the third thing is that now that we have assumed that this is true, now that we have assumed this is going to be true, all we have to do is show that P of K plus 1 is true. Because if we can show that this statement is true after assuming that the general statement is true, well, that means who's to say the K plus 1 idea is that, okay, if it was true for 10, and we showed that it was true for, yeah.
So what if your base case is, say, what if whatever you're trying to prove has division in it, and your base case is -1, and then you assume that PK is true for anything greater than -1, but when you get to 0, there's a undefined.
That's a good point. Well, yeah, because there are domains of where proofs are true. And so that's why when you happen to read math theorems, they tend to get more and more and more lengthy because they have to include more and more and more caveats, because the more math you learn, the more complicated you're allowed to realize and learn that it actually is. And so you can include all of that rigor. And so what happens is then you would then be trying to show by counterexample that this is not true if you can find a range like that, like you're saying, if you suddenly get to 0 and then it breaks. If you can show that, you have also answered the proof. You've solved the proof by saying contradicts, therefore this is not a true formula. So that is also a valid result.
But you could go through the whole induction proof as stated here, and all of this would check out,
Well,
right?
not exactly. So I like what you think. So let's think of it like a number line. So if we have here 0, say that 0 is the breaking point. So say that this is where trouble happens. It doesn't work at 0, but it will work for the negative numbers and it will work for the positive numbers. So it'll work, broken, will work. So what happens is this is going to answer your question. However, we restrict the variable or the parameter or whatever we're talking about. So if I would have said n includes the reals, we can prove by counterexample that this is false. We can prove that this is not a true statement because we're now including the trouble spot, 0. But you can, it's a different, so that's where we got to differentiate statements. And that's why when you do induction, it's super, super important to define. So P should be a well-defined statement. Because if our statement Pn is that this formula holds for all of the reals, well, that's a statement, but it's a provably false statement versus this formula holds for only the n being positive integers. So do you see how those are completely different statements and then they end up giving you different results? So ultimately, it doesn't really matter where it will hold and where it doesn't. So long as you're choosing basically the interval of where it works, that's really what we're trying to say with this condition. So hopefully, does that make a little bit more sense?
Yes.
Okay. And yes, it's abstract. It's difficult.
But
Is there something I could do to explain it a little bit better?
well, I'm thinking that, like, say I had
So are you thinking maybe if we were like, what if n was allowed to be a real, so that means pi. So all irrational numbers then would technically be n, right?
Right, but then what you can do is you can go through the steps and you go, okay, P1 is true. You can prove it, I mean, it's a real number. And then you
Oh, I
can
see.
assume that PK is true and show that P of K plus 1 is true, and all that works out. So how do you know you've picked the wrong set without?
That's a good question. And what's really cool about math is that it works, which means that this assumption, so when we make an assumption, that doesn't mean it actually has to be true. And that's kind of the beauty of when you do a proof. You can assume something that's not true. And then the result you get out of that is just a reflection of that untrue statement, right? So if you were to assume, and so if now this is not an untrue statement, this is impossible to do, actually. When you try to get to this step, you will never, ever be able to get this to be true with this assumption.
Or because it's not defined.
Exactly. So you will never have to deal with a circumstance where you do succeed in proving this equivalence between this assumption and this result, if it actually doesn't work. So if this is actually false, you're not guaranteed to find this. And that is the result of the proof. Then you basically say, thus P, K plus 1 is false, does not exist, or contradicts the assumption. And you can't have a contradiction with this assumption, meaning that then it's false instead of true. So it's very binary between true and false. So does that make a little bit more sense?
Yeah.
Awesome, cool. So we can implement this strategy directly onto the sum of the first and our positive integers. So to give a little bit more space here.
Imagine a nice sign like that. Like CV.
Yeah.
But it's the newer version, so I don't know if everything's right. It's the first, okay. 1.1 was moved to 1.2 in like the newer
Yes.
version. So-
Actually, and if you guys don't have the book yet, I finally got mine, so I can take pictures of it and then I try to somehow get that out to everybody.
I found a PDF online, but it's
Yes, I also
It's, yeah.
2002 version.
The 2002 version is, I think, the fourth. And so what happens is that the complex, they merged 1.1 with the complex. So 0.4 wasn't exist and then they pushed it. Then the exercises are still correct, but then it's like the actual content you're reading is kind of jacked up. Wait, hold
But
on.
the
Yeah.
exercise is in a different,
It's
section.
1.2 rather than, they added
Yeah.
1.1, which is a different section.
So,
to 1.2.
it's-
So you gotta go one letter.
Yeah, because it would be so when you read the syllabus, don't go by the section number if you use the PDF, because the content's basically the same. So as long as you know the topic. So it's like 1.2 for the 6th edition is isomorphic binary structures. So if you use the PDF, you just scroll down and be like, okay, where does it match with isomorphic binary structures? Or whatnot? Yeah. So, okay.
Hopefully it's all this time.
So the first thing we need to do, so when we do, we have the scratch word portion. Portion of a proof. This is the stuff that you're going to do on the side that you're not necessarily going to write in the proof, because ultimately, at the end of the day, you can think of that proof as being like this nice, final, polished product. So we got to figure out the inner workings of this stuff so that we can just present it in a clear fashion. So we are going to assume that P1, well, we don't have to assume it, we can directly compute P1, right? So P1 is 1. And then what is the formula, right? So if we evaluate the formula that we're trying to prove at n equals 1, then we get 1 plus 1, 2, 1. So it's not rocket science, thankfully. And so basically all we have to show is that, okay, P1 is true. And then essentially we should really say thus, because this word signifies that the math that you just did is the reason why you can say that P1 is true. Some people like to say that P1, like they'll put P1 equals 1 plus 1 over 2, but this is kind of unnecessary, so I wouldn't worry about doing that. So we have the first step. We have our initial thing. So P1 is indeed true. And then now we're going to assume. What are we going to assume? Right. So some PK is true, but make sure you finish that statement. K is what? Has to be greater than 1.
Yeah, and non-zero.
Right. And so K is 1. So this is answering your question, how we
Yeah.
can exclude. So this right here.
That was
So
awesome.
what happens a lot in algebra is that people would just get into that mechanistic, like, okay, I gotta get exercises done. So they'll write this down and then they'll leave this out, which this kind of is super, super important. So you might be wondering, okay, now that we've assumed that, what good is it in assuming that that's true? How do we use that? Well, K is just a number, right? So there's nothing stopping us from just doing a direct computation. So if we want to evaluate PK, what is PK? Well, it's going to be 1 plus 2 plus blah, 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 plus K, and whatever K happens to be. It's greater than 1 and it's a positive integer, so we're good there. And this is what we mean by assume this is true. We can actually assign K plus 1 over 2 to this number right here. So this is our assumption. We have to assume this. If we don't assume anything, we can't prove anything. And then now the third thing we gotta do is we have to show that PK plus 1 is true. And note that I don't really need to add this on there because it's implied that the only thing that we're still dealing with is this K, which is obeying these properties. Okay. Do you have, so anybody have just any wild ideas before we finish this proof of how we could show that this statement is true?
3 plus K plus 1.
Exactly. We can just directly compute this and then see how it lines up, right? So if this were to be true, what would this look like? So in other words, if this statement is actually true, it will satisfy the formula. So remember the general formula was n plus 1 over 2. So if this is true, that means this, whatever the number K plus 1, that's just one number, K plus 1 has to satisfy this formula. So in other words, we're looking for some K plus 1, so that's n, times K plus 1, so just K plus 2 over 2. So in other words, we're going to directly compute this from the formula and using our assumption. We're going to manipulate. If we can show that we can eventually manipulate down to this, then we have shown that PK plus 1 is always going to be true. And then by nature of this being true and this being true, we can make the statement that for all the n, Pn is true. So this that's why it's super important to do scratch work, because it's really hard to sometimes eyeball. The formula is not always super simple. So you won't always be able to eyeball what you're trying to induce PK plus 1 into. You need to figure that out so that you can strategize the way you juggle down the algebra once you compute that. So now we're just going to do exactly that. We're going to directly compute PK plus 1. So what we have PK plus 1 is 1 plus 2 plus blah, blah, blah. And you brought up a really, really good observation. We can stop it right at K because we know what this is. That's just a number. And then we add on K plus 1. So this is really, really the same thing. We've just kind of put parentheses around to highlight the trick that we're going to exploit here. So that was a really, really good observation, Renee, because we assumed something about this. We made an assumption.
That's true.
That is a truth. So we can now use that assumption in our computation. So what is this? What does this reduce down to given our assumption? Right, it's just K. It's 1, 2. But, and then now we're adding K plus 1 to this. Okay, well, One thing that we can do is we can divide, we want a common denominator, so we have to multiply the top by 2. So we have k, and then let's see, we have k plus 1 plus 2, k plus 1, all over 2. Okay, great. Now notice this is why we did the scratch work, because now we actually have a reason, we have something to motivate how we're going to reduce this. So k plus 1 is right here. Factor out k plus 1. This should look familiar because this is precisely what it should have been, assuming that the assumption is true. You see that? And so this is a really, really powerful. So we have essentially completed the math side of the proof. And so when you go on to write the proof, I'm not going to take super long on this, but it's definitely worth discussing. So now that we've done this scratch work phase of this inductive proof, because I think a lot of times that when students take their first course in algebra, is that they kind of forget how powerful words are. So words are no longer kind of just a little bit free form. They actually have very explicit connotations and meanings attached to them. So what we're going to do is we want to show that 1 plus 2 plus 3 plus blah, 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 plus n equals n plus 1 over 2. At the start of a proof, you should state what you're trying to show, because if you don't show what you're trying to show, you have no logical impetus to continue down in the proof. Now, after that, we need to define some things and then assume. So we get all the definitions and assumptions at the start. So we're going to define. So let P of n be the statement that the formula is true for all n in positive integers. Why is it important to define Pn at the start here?
Because, well, first of all, because you're going to work with it the whole time, but also so that you have assumptions to work with.
Exactly. If you don't define what your statement is, well, like, that could be anything. If I just use randomly stick a Pn, someone reading the proof is like, whoa, hold up. No one told me what this is supposed to be, so I have no idea how it's supposed to logically interact with the rest of the elements in this proof. So we show, and note that this is a statement because it can be provably true or false. And so don't get in the mindset of thinking that true is better than false. They're both equally good. And the point of math is just, can you even show one or other? You know, it happens to be the case. So here is our here's a definition. So you don't have to don't include the stuff in the parentheses in the proof, but you can see kind of the structure of what's going to go on. And so we're going to be now we just show the P1, so the explicit computation. So we see that this phrase, we see that, is how we kind of denote something that does not need to necessarily be proved. It's more, we use that for computations if we're going to do an explicit computation or an example. So we show that P1 equals 1 and 1 times 1 plus 1 over 2 equals 1. Thus, P1 is true. So this is now establishing. So this is particularly with induction. We're showing a base case is true. So we see that blah, blah, just compute that. This is normally super easy, and then just state. Don't forget to state though that this is true. Because if you never state that P1 is true, then by the time you get to your conclusion, you're not allowed to yet say that Pn is true because you didn't even guarantee that this was true. So now we make the assumption. So definition, we show a base case. Now we're going to make an assumption. Yeah, assumption was what? Yes, so let, and so the word let is often used as kind of like if you're about to make a definition or an assumption, but more commonly it's an assumption. So let PK be true. But then what was the condition for K here? We can't just let K be anything we want it to be. Right.
Greater than 1 and belonging to the integers.
Right, K greater than 1, K positive integers. Okay, great. Now that we've made our assumption, now we're in the proof section. Okay, so now we are in the proof section where we're actually going to do. And so now, since we did all this handy dandy background work, we know exactly what we're about to segue into. All we've got to say, the statement that's going to segue us into this math right here, is that after this, we got to show the important result. How do we use this result, right? So then 1 plus 2 plus up until K is equal to K plus 1 over 2. We do have to state this, because if we don't state this, then you can't use it later on. So proofwriting is actually a really, really straightforward process. You can't say stuff that you haven't defined. You can't use terms you haven't discussed, and you can't assume things that you haven't already said that we're assuming. So it's although it can seem really nebulous because the problems vary so greatly, but really at the end of the day, just make sure you're keeping track of what you've defined, what you've assumed, and then just go from there. Now that we've showed then this, okay, now we show that, and then the thing that we're trying to show, PK plus 1 is true by computing the following. And then we just compute. And then lo and behold, we get this, which is precisely what it should be if it is to be true. Here's the key thing for you guys to see. You don't have to know in the scratch work, we worked out what we need this to be in order for this to be true. You don't have to do that in the proof, because when you write a proof, especially in higher maths, it's assumed that the reader is conscious enough to know that this means that this is true. And also K plus 1 is true. So they would just mentally substitute K plus 1, see that this works. And so always you can just finish up the proof. You could just say, and then so the conclusion. It's just basically therefore or thus. And then state what you just proved. So then therefore P, because at the end of the day, what we were actually trying to prove is Pn is true. And then Pn happened to be this very particular statement. But basically, therefore, Pn is true for all n in the positive integers. And then that is a proof. I like to end my proofs with a box with 3 lines through it, but there's absolutely no, that's just kind of like, it's like having a signature in math every single time you finish a proof. So yeah, QED is what some people do. That's kind of like how they finish their proofs. That's a personal choice you can write.
Dr. V doesn't like writing without the lines.
Yeah, my friend, I have a friend, he's a topologist guy. He likes to just do the open white box at the end of his proof. Some people do a black diamond. Isn't
that what Dr. Lemon does? Just the box?
I think, yeah, he does a box or, what, I'm trying to remember what he does.
I'm pretty sure he does
I'm
box.
pretty sure, yeah, he does box. So is this all good? So I'm going to assign a problem that we're not going to do in class, because if you understand this conceptually, it'll take you 10 minutes to write it out. It's a very, it's a good exercise though, to make sure you understand the piecework of it. Logic. Okay. Problem to work out is going to be. All right, so in your own time or right after class or whatever, because it really won't take that long. Prove that the formula is true. And so what we do is we take 1 squared plus 2 squared plus 3 squared plus up until the nth square. So the sum of the first n perfect squares is equal to n plus 1, 2n plus 1 over 6 for n in the positive integers. So try proving that this is true with induction. So prove with induction. And then on Friday, we'll go over your solutions for that. Sound good? Awesome. Okay. So in the remaining time, we're going to, so I know that all of you have already done the exercise for 1.1, but there is some really, really good just proof writing stuff in general to be learned so the first like 6 were not that bad, right? It was fairly almost trivial. You just substituted blah, blah, blah. How did you guys feel about like 36, 37, those last 2?
They were tough, but I mean, took a little bit of thinking. But
So do you have this written down?
yeah.
Okay. Because what's good is I was kind of hoping that you had done the problem before coming to class, because then we can actually talk about some of the more important abstracted and workings of these concepts, because these are really beautifully written problems, honestly.
36 gave me a little more trouble than 37.
Right, 30 because that binary operation is a simpler binary operation. It's more well behaved, right? Okay, so we were supposing that we had a binary operation that's associative. So star is an associative binary operation on a set S. And then we were showing, so show that set H is elements A in S such that A star X equals X star A for all X in S. And so this is a really cool set. Something that they didn't really tell you in the text, and it comes up later, is that this is a very, very specifically defined set, right? And this is what we call the center. It's the set such that you take all elements that in the set commute with every other element in this set. Very, very specific, very well-defined set that comes up later on. Okay, so we want to show that this is closed under star. So when you look at a problem like this, right, you have to consider a few things. First of all, what the heck is closed under? Because if you have no idea how this is defined, then obviously the proof for this problem is going to be very difficult, because you have no idea what you're even trying to show. And so the crux of this proof, really, to get past the mental block, is interpreting what you're trying to show. So remember earlier, at that first step, we had a want to show something. If we have no idea what we're even trying to show, we don't know which definitions to use, and we don't know what assumptions to make. So what is the definition of closed under? So if a set basically is closed under star, what does that mean about that set?
Means that every result of the operation is a member of S.
Right.
Of
So
member H.
if we have A, B in our particular set, we also have to have A star B is in that set. So if we can show that these two things are true, then it's closed under a star. So we know what we want to show now. And then how can we go about that? So what's really cool is if you have A and S, A star X, this is just a property that it must satisfy. So what we're really doing is we got to identify that this is true and that this is true. So E, B, and S, we can automatically show that A star B is in S. Why can't we immediately make this statement off the go just from what's given to us in the problem statement?
Because of the definition of the set?
Close, it's the definition of this, because the definition of a well-defined binary operation comes with it. So this can only be well-defined if and only if you take two elements in that set and then use that operation, you get something inside the set. Yeah.
I think, don't we want to show that it's, I think that's where it's closed under S, we want to show it's closed under H.
Oh yeah, sorry, I
I
was
said
doing
that,
that
I
as
said
an
that.
arbitrary example here, but yes, we put it. So in this case,
No, I think I said that, but then
right. So for this particular problem, but remember, at the end of the day, the point of abstract algebra is the structure of these abstractions. So, I mean, these symbols are very, very arbitrary. I mean, who's not to say that that is a letter, right? So there's, what's really fun is that then you can start trolling all your friends and then start doing math with made up objects that you want. And then it's really funny. But so A star B is an S because this is an associative binary operator on S. So in a sense, we're using this concept of taking something that's been assumed and making a conclusion based off of it. Okay, now the tricky part obviously was showing that this statement was true, right? So A star B is in H. The first thing to note was that you have to mentally see A star B as a single element. Because if you try to see A star B as like something like, oh, I have to keep the operator involved, you'll get yourself really confused really quick. So this is really just one element. And what does it mean for this element to satisfy the conditions to be in H? Well, it's got to commute with everything in S. So if we got to show that this can commute with any other element. So do you see how this is not associative property? Because it looks like it could be because we have 3 things equals 3 things, but it's really this element star this element. If you were to rearrange the order of those 2 elements, this is commutative. So this is a restatement of the conditions for it to be in H. And then obviously, so all you got to do is you do end up using the associative property. You start here, you state the associative property, and then you juggle, and then you're able to show that this is true just by knowing that it's associative and commutative, associative, commutative. So I'm not going to spend too much more time on that because there's one more example before time runs out. And so it's this idea higher, it's easy to think of an operation, especially even in abstract algebra, it's easy to think of an operation as we kind of go back on our crutch of, oh, it's like plus, or we do it by analogy to something that much less abstract, right? But a function, an operation is really a function. You have to see it as a function. So is a function. And this observation was really, really crucial for doing, let's see. So like question, it's question 12, I believe. Oh wait, no, not 12, sorry. It was question 13. So it's how many different commutative operations star
This was your first one.
can be defined on a set with exactly, and then 2 elements, and then they had you do 3 and then n eventually generalize it to n. So the idea with this is you had to recognize that, because conceptually, without this, you're kind of stuck. There's not really other ways to show this. So it's a very specific function. So star is a very specific function that maps the Cartesian product with the S with itself, and then it maps it just to S. And so what's really cool is I like how they wrote the problem to build it up so that they just didn't smack you with do it for n elements in a set. If you took so if we were letting this number, the number of sets of the cardinality of S were to equal 2, we can directly, this implies, what's the cardinality of S cross S?
4.
Yes, exactly, so 4. Because this Cartesian product takes every combination of basically those 2 elements and then you map it into, yeah. So basically we can show that, abstractly, S cross S has 4 elements. And S has how many elements? Just 2. So really what we're looking for is we're looking for some sort of function. So you reframe the question into something that's a little more straightforward. Instead of saying, how many operations can we define? We're saying, well, literally, how many one-to-one functions, how many ways can we map S cross S onto S? And so then now you think about, okay, so for this element, because every single one has to be accounted for, this, how many options does it have to be mapped to? You can map it to how many? Okay, so we have 2 ways we can map that. What about for the second element? And then, shocker, all 4, we are allowed to go to either of these 2, right? And actually, that's a lie. That's if we're dealing with a non-commutative. So if we have a commutative, I should have specified this. If we have a commutative, we do actually need to be aware of what these are. So if we have some A, B, and then A, and then B, A, and then B, E. So A, B can map to any of the 2. A can map to any of the 2. What about BA though? Does BA have a choice? No, why?
Because it has to be commutative with AB.
Exactly, so it has to map onto where AB was mapped onto, so it always got one option. And then BB though, could be any of the 2. And so you end up getting 2 to the 3 for this case. When you expand this to n, you can illustrate this in different ways, but you can do it with like a matrix or just straight computing. That if you have the cardinality of S starting as n, what does that imply about the cardinality of your cross product?
Squared.
Exactly. You have n squared. Now we want to take how many elements, note the pattern here. This is a unique element, AA. That's only going to compete with itself. So we don't have to worry about that. And there's going to always be exactly n of those. So we can take n squared, which is the total number of things in this set, and we subtract away the n. And that's going to be what then we have to divide that in half. Because that's going to be like AB, for every AB, there's going to be a BA, and for every CD, there's going to be a DC, et cetera, et cetera. So when you actually then exponentiate this out, you really just have the n that are in the form of this, where it's the same element. They could go to any of the n in the cardinality of S. But you also have to now account for the other guys. So then there's going to be n, and then n squared minus n over 2. And the reason that this is a really, really cool number, I'm not sure if you recognize this, but when you do resolve it, you end up getting n plus 1 over 2. And that's really, really cute because that's basically just the sum of the first n integers. So that has it, that shows up. Anyways, that was more just like a fangirl moment for math. But anyways, so hopefully that was helpful. Tomorrow, we're gonna talk about, Friday, we're gonna talk about isomorphic binary structures. I'm gonna email Dr. Lang and ask him, like, since it was really weird this week when he got sick. So 1.3 is probably not gonna be due on Friday, simply just because we didn't have Monday lecture to get through this stuff, so. If you guys have any questions, just let me know. Yeah, probably just 1.1 and 1.2 for Friday. And also that problem, that inductive proofs. Just bring that on a piece of
So
paper.
break the inductive proof, Jenna.
Yeah, yeah.
Thanks, Dr. Allens.
Yes.
I don't have my doctor.
Yeah.
In my mind, you do.
Well, I wish I did someday.